Hello, my name is Nick Perello, and I am going to talk about our work on marrying fairness and explainability in machine learning. This is a joint work with my advisor, Przemyslaw Grabowicz, and my peer, Aarshee Mishra at UMass Amherst. With the rise of automated decision-making systems, one of the most rapidly growing research areas in machine learning is how to measure and prevent discrimination. That is, how can we ensure that machine learning systems do not treat someone unfavorably because of their membership to a group characterized by protected features such as race or gender? Surprisingly independent from this, another increasingly popular machine learning research area is how can we explain these often black box systems to appropriate trust and improvements for them. For instance, given some sample in a machine learning model, how impactful was each of that sample's features to their predicted outcome? With the gap between fairness and explainability literature, it is often left unexplained how fair machine learning solutions work with respect to legal instruments, thus creating a barrier to the widespread adoption of such solutions. For instance, this connection is still a work in progress in one of the first and best books on fairness in machine learning by Salom Barocas et al. That many of you may have already heard of. Therefore, our work bridges this gap by joining fairness and explainability solutions together with legal text. Before we present our solutions, we must first understand the current challenges of fair machine learning using ideas from explainability and fairness text. Perhaps one of the most basic solutions is the idea of dropping the protected feature when creating a machine learning system. This would be analogous to someone saying they are colorblind when it comes to racism. This idea, however, remains discriminatory as the system can just find a proxy feature for the drop protected feature. For instance, as many of you know, redlining was a major problem in the United States during the 20th century. Using feature impact measures, we can present redlining using explainability literature. First, we can start with a model that directly discriminates and is impacted by race. Then, we can modify this model by dropping the impact of race, thus resulting in an increased impact of zip code as it is being used as a proxy for race. In other words, we are now redlining. On the other hand, many of the solutions popular in the past decade have been based on enforcing some notion of statistical fairness. For example, the notion of statistical parity, where members of each protected group have the same chance of getting a positive outcome. While this may achieve a balanced outcome, these solutions might drop the impact of features related to the protected feature that is necessary and legally allowed for decision making. For example, in the well-known Berkeley study of graduate applicants, it was found that men were accepted more often than women, which without context seems quite unfair. However, this can be partially explained by the fact that women often applied to more competitive departments than men at Berkeley during this time. If we built a system that tried to enforce statistical parity here, it may drop the impact of department choice to equalize the chances for men and women getting accepted. Therefore, we propose a solution where we drop the impact of the protected feature on decisions while ensuring the impact of the remaining features remains the same as the original model. This can be achieved by tying our work with explainability and causal influence literature to measure impact and then create relevant loss functions. With the ties to explainability literature, we can define discrimination in such a way that our methods have direct ties with legal instruments. Now, in the context of the example shown before, our solution in the redlining case removes the impact of race from the original model while leaving the impact of zip code at none. Meanwhile, in the Berkeley example, our solution will leave the impact of department choice the same as the original model. Before defining how to measure influence, we first define a couple of abstractions of legal instruments. To start off with, we first define unfair influence to be the influence of protected features on the decision that is deemed illegal by some legal instrument. For example, one legal instrument can be the Civil Rights Act of 1964, which banned employment discrimination based on race, color, religion, sex, or national origin. Conversely, we define that a fair relationship between non-protected features and the protected features to be one that is just legal for some decisions. In the Berkeley example, this can be the relationship between sex and department choice. An example with major legal precedent is the well-known Ricci versus De Stefano Supreme Court case, where the majority ruled that the promotion exam in question did not violate business necessity. Thus, according to the court at least, there was a fair relationship between the exam and race. These notions, we can measure influence using explainability or causal influence measures and create influence-based definitions of discrimination. For instance, we can use controlled direct effect or CDE, a standard causal influence measure that at a high level measures the expected change after intervening on certain features. Now that we can measure influence and know how to determine what is fair or not, we can now define discrimination. Unsurprisingly, direct discrimination is the unfair influence of the protected feature on decisions. So in the housing alone example, the original model would be directly discriminating via race. We'd ideally want CDE to be 0 after intervening on the protected feature. In the real world, it is often the case that there is an unfair influence on other features and decisions from the protected feature. This is called indirect discrimination. For example, take the gender pay gap currently prevalent in modern society and a hypothetical loan approval system. If pay influences whether or not someone gets approved for a loan, then we have indirect discrimination via gender's unfair influence on pay. This discrimination can be removed via nested usage of our method on the features causing it. More details can be found in our paper. Next, we define discrimination as a difference in the influence of features dependent on the protected feature between two models. This captures the issue of redlining. First, we have a model that is not influenced by zip code, but directly discriminates. So we decide to create a new potentially non-discriminatory model that drops race. However, as expected, the new model is influenced by zip code. This change in the influence of zip code is induced discrimination. To create loss functions that achieve our goals, we use two different influence measures. One is a marginal version of CDE that we introduced called marginal direct effect, or MDE. We explain in our paper its advantage over CDE. The other is Shapley additive explanations, or SHAP, which is one of the most popular explainability measures from literature. With these notions, we create a loss function that preserves the influence of non-protected features while removing the influence of the protected features from the original model, or in other words, to prevent direct and induced discrimination. So to reiterate the goal of our loss function, we want the influence of the protected feature to be 0, while the influence of the non-protected features remains the same as the original model. To minimize these loss functions, we proposed a marginal interventional mixture, or MIM. This takes the outcome from the original model and finds the expected outcome over the marginal distribution of the protected feature. In our paper, you can find our proofs for how this minimized the MDE and SHAP-based loss functions. We test the following methods from all stages of a machine learning pipeline: pre, in, and post-processing. All methods but the MIM and traditional dropping Z are based on statistical notions of fairness. Traditional dropping Z is the original model but with the protected feature dropped during training. More information about these methods can be found in our paper. We test the MIM and the other methods on synthetic and real datasets. In this talk, we present results using SHAP. You can find MDE in our paper. The synthetic dataset is a simple scenario with three features. Notably, one is the protected feature Z, and another is a feature X1 whose correlation with Z can be adjusted. This lets us observe how methods handle potential relations between the protected feature and its proxy. Our baseline or original model is simply logistic regression using all features available. In these synthetic scenarios, we plot the expected influence on the y-axis and the correlation between x1 and z on the x-axis. As expected with our loss function, the MIM preserves the influence of the baseline model traditional with z. That is why you see the red and blue lines overlap in the influence plots for the non-protected features x1 and x2. Meanwhile, the MIM drops the influence of the protected feature as seen by the red line at 0 for the plot of z. Then, we add the results of the traditional model trained without z as a dotted blue line. We can see that it is exactly like the naive solution described in the beginning of this talk. The impact of z has been completely dropped, but as we increase the correlation between x1 and z, this method is increasingly impacted by x1 since x1 is becoming more and more of a proxy for z. Finally, with all the methods shown, our method is the only one that preserved the influence of the non-protected features while dropping that of the protected feature. We explain why other methods don't preserve influence in our paper. Additionally, even though our method did not optimize for demographic disparity, we found that it resulted in fairer results according to that measure than the original model at high correlations. Meanwhile, the MIM was the most accurate of the fair learning methods that had less demographic disparity than the original model. In our paper, we present real-world results using the adult census, German credit, and COMPAS datasets popular in machine learning fairness research. In this talk, we'll focus on the COMPAS dataset, which we've modified to exacerbate racial bias. For COMPAS, outcomes are whether or not a defendant will recommit a crime, and the protected feature of focus is race. The two features most correlated with race are the number of prior counts and age. We plot the influence of these three features below. Our method preserves the influence of the features most correlated with race while dropping the influence of race from the base model. The dotted green line shown now is where our fairness objectives wants influence to be at. As we can see, the other methods don't simultaneously accomplish both. The OPT method shown here is a more complex variant of the MIM that we introduced in our paper, yet it achieves similar results. As with synthetic results, our method eliminates some of the demographic disparity while maintaining good accuracy with respect to the original model. The results here and in the previous slide generally hold the same for the adult census and German credit datasets, which can be found in our paper. As with all fair learning objectives and methods, there are concerns we have with our work. Firstly, users can omit the instructions for removing indirect discrimination via nested usage of our method. This will lead to indirect discrimination's preservation. Additionally, our fairness objective, like all others, can be misused by people to justify that their systems are fair. If the original model was developed in bad faith to hide the discrimination of the true model, our objective will preserve this unfairness. Therefore, we emphasize collaboration with domain experts and audits of these systems to ensure the validity of their assumptions. To summarize this talk, we first defined discrimination based on influence measures and legal instruments. Then, we created loss functions and methods that minimizes this discrimination. And lastly, we showed how our methods compared with other fair learning methods in synthetic and real-world datasets. Thank you for watching, and we hope to hear any questions, comments, or feedback you may have.